This brief lecture is inspired by a question from a student in the class. So, why is that some batteries have a separate chamber for anode and cathode separated by a junction, but some other batteries do not seem to have an explicit junction, separate chambers? So let's just look back at the context. So, for example, when we looked at the lead acid battery, the lead acid battery does not have explicit separation. Okay, that is, the anodic chamber is not separated from the cathodic chamber, or the positive electrode is not explicitly separated from the chamber adjacent to the negative electrode. So this has to be looked at in some context. First, let's look at the reactions, relevant reactions for the lead acid battery. So on one side, lead oxide is getting reduced to lead sulfate, and the lead sulfate is just deposited or formed adjacent to the lead dioxide. In a way, this also separates, this layer separates this from the electrolyte. And then on the other side, lead gets oxidized to lead sulfate. That is Pb0 goes to Pb2 plus. So that is the reaction occurring on this side. Again, lead sulfate that um, is formed adjacent to lead and gets deposited adjacent or on top of the lead electrode. So the overall reaction is this one: lead uh, plus lead dioxide and the giving rise to lead sulfate and so on. So let us understand this in a particular context. In a previous lecture, we had mentioned that this is not the way to make a battery. That is, if even though zinc and copper are proper materials, a pair of materials with appropriate reduction potentials and redox couple, if you make a battery, you will, like in this manner, that is, the zinc rod and the copper rod dipped into a solution of zinc sulfate and copper sulfate. If you make a battery like this, you won't really get a voltage. Okay, so I mean, you won't get a voltage that is like a battery. Okay, so there will be some difference in work function, which will show up in the voltmeter, but significant potential will not be seen. Why is that? We said that when you have this kind of a system, copper 2 plus that is present in the electrolyte will collide with this zinc rod, and zinc will get oxidized to zinc 2 plus and copper will get reduced to copper. So even though there is electron transfer in this process, that is, Zn reacting with Cu2 plus gives rise to Cu plus Zn 2 plus. This exothermicity associated with this particular reaction just goes as heat. Okay, it doesn't go towards performing electrical work. So this has to be separated in two chambers. That is the relevant electron transfer reaction. One is this, another is this. They have to be done in two separate electrodes. So this copper 2 plus cannot collide with zinc rod here. So this has only zinc sulfate solution, and this has copper sulfate solution, and this okay, and there is a salt bridge to maintain electron neutrality and so on. Okay, so there is an explicit separation of chambers, which is not seen in this battery chemistry. Why is that? So if you look at the appropriate reaction, it is easy to rationalize. See, even though you write the overall reaction like this. In this battery, lead is not directly in contact with lead dioxide to make possible this reaction. Okay, so this is the just a way of writing the overall reaction. Okay, given this kind of physical configuration, there is no way lead will react with lead oxide and give rise to lead sulfate. Okay, so if this lead is put here, okay, even then the lead is a solid. Okay, so there is no collision between lead and lead dioxide giving rise to lead sulfate. Okay, so that is the main reason. Here, the relevant reactants, okay, so in this case, zinc and copper 2 plus could collide and give rise to a redox couple, but such a possibility does not exist, okay, because lead dioxide is not directly colliding with lead, uh, giving rise to a redox couple, or lead is not colliding with lead oxide, lead dioxide, giving rise to appropriate redox couple. Okay, so there is no deposition of any material from this electrode directly. Okay, so that is the main reason. So you have to look at this question of the reason for separation of into two different chambers from a more functional point of view. Okay, so what is happening at each of the electrode electrolyte interface? So that is the main reason. And so in this case, this is a bad geometry for a battery. It has to be separated into two different chambers. Okay, for example, even if you don't have a salt bridge, you can have a separation of chamber. Okay, so this can be a separator which does not allow cations, but which allows for the transfer of anions. Okay, here the sulfate is the relevant anion. So that will get transferred, but it will suppress the transfer of the cations. What suppresses this separator? So even though you don't have a salt bridge, this kind of separation of one chamber from the other chamber is still a appropriate configuration for a battery. So introduction of these kind of separators as well as a salt bridge have consequence. It is um, this electrochemical consequence of a separator has been elaborated in a previous lecture. So this kind of a junction will give rise to a junction potential. Okay, so how do you think about the potential across this junction was covered in an earlier lecture. Um, um, this is the title of that lecture. You can look at this lecture to understand um, the basis for Henderson equation. So the so-called junction potential, it depends upon the mobility of the relevant anions and cations, and the and few other um, um, parameters. Okay, so this has been analyzed, and this Henderson equation and this junction potential is rather interesting because this potential comes rise due to a kinetic effect. Okay, not necessarily due to a thermodynamic effect. So because mobilities are involved, okay, or kinetic or transport quantities. So in most of the potentials you see in electrochemical systems, there um, there is not an explicit reference to a transport related property. In this case, the potential depends upon the mobility of ions. Okay, so these are probably jargons unless you have heard this lecture. So I would encourage you to go and look up this lecture if you're not familiar with certain details of electrochemical thermodynamics. Okay, so there are two important topics, very important topics that are covered. This Poor-Bay diagram is very, very critical. So for every electrochemical system, this is of vital importance. This provides a fundamental way of looking at the electrochemical thermodynamics. In addition, these junction potentials are also seen in many systems. So I encourage you to just go through this lecture also to understand what we mean by Henderson equation and how is that relevant for the junction potential. In the next lecture, we will look at the theoretical capacity and an important quantity called state of charge in a battery system. That will be the